Okay, so welcome to Math 381 for fall 2020. I'm happy to see so many students. I'm also very happy that I was able to move this class online for our safety. Um, so what I want to do first is to go over the syllabus. Did everyone get a copy of the syllabus via email, or is there someone here who was not able to get a copy of the syllabus? Seems like everyone got it. Okay. Well, let's see. What I'd like to do is share the syllabus so that we can discuss it. Okay. And of course, I may have made some mistakes on the syllabus. So let's go through and find out. Here's my email, marmark@live.unc.edu. This was funnier 6 years ago when I was coming in. My name is Mark. I'll be your instructor for Math 381. I'm not a professor, I'm just a grad student, so just Mark will be fine. No need for Professor Besson or anything like that. Just Mark, please. As you all know, this will be a totally remote class. So I wrote this section a little while ago when I was still unsure whether or not I'd be able to move this class online. So all the lectures will be available on Zoom. What I really ask is that you come to the lectures as I am lecturing, so 9:20 to 10:10, Monday, Wednesday, Friday. I think that there are several good reasons for this. One is that it permits you to ask me questions. Sorry, I think I'm going to sneeze. Maybe in a bit. Okay, one, it permits you to ask me questions. Okay. Two, it provides some sort of schedule and some minuscule amount of social interaction, both of which I think are very valuable. But mostly the important thing is to be coming consistently, keep track of the material, be able to ask questions on the material as it comes up, etc. So I'm going to be holding pretty strictly to the schedule. The good thing about having everything be online is that I can record my lectures and immediately put them on YouTube. So I will be doing this. If you miss a lecture for some reason, if you have stuff going on at home, like if you have any issues with actually attending the lecture at lecture time, you can watch the recorded lecture, and this should help you not fall behind if for some reason you can't make a lecture. And I will send y'all the link once I post the first video. There are also some videos of my last class that I taught. So I taught 381 in the spring as well. So there are kind of old lectures of mine on this subject that you can find too. All homework will be submitted and graded via Gradescope. I sent this document out, so you should have access to this course on Gradescope. Did anyone have any issues with getting registered with Gradescope or joining this course? And you'll have to speak out at this point because I can't see the messages that you write right now.
It doesn't, were we supposed to register ourselves? Because my chemistry classes registered me automatically. I don't see Math 381 online.
I did not register you automatically. I sent a code that you should put in to register yourselves.
Okay, I'll work on that then.
Cool, thank you. Okay, so we have a grader for this class, and they'll be grading the material, but you're free to ask questions of me, and you can talk to me about the grading of the homework and stuff like that. All tests, including the final, will be administered online. So there will be a grader for the homework, but I will grade all of your exams and your final. So that's an important remark that I want to make. And all office hours will be held online. Okay, so everything is online. I'll make some more remarks about how tests are going to go. Everyone who's here knows that the class is Monday, Wednesday, Friday, 9:20 to 10:10, because you're all here with the correct Zoom meeting ID, so that's great. The textbook that I'm using is Discrete Mathematics and its Applications by Mr. Kenneth Rosen. I can show you my copy that I have. Oh yeah, you can't see this yet. Anyways, it's the 8th edition. The 8th edition is only important in the sense that I'll be assigning homework problems from the book. I recommend that you find some sort of discrete mathematics textbook, but I don't necessarily recommend that you buy any textbook at full price. I think in general, textbooks in college are a huge racket by publishing companies. So really the two important things that you need out of a textbook is, one, you need some sort of discrete math textbook so that you can read about the topics that I'm covering, and two, you need access to the exercises that I will post on Sakai. Whatever manner or whatever way you find to get access to those two things is sufficient. If you have a friend who has Rosen 8th edition, then you can use their problems in the problem section, and you can use any old PDF that you find online for a discrete math textbook. So I definitely want to save y'all money. So if you can avoid buying a full discrete math textbook, do it. You just need to have access to problems and some sort of textbook. Any questions about that?
I have a question.
Yeah, sure.
Will there be like a set reading schedule for the textbook so we can read ahead if we want?
Yeah, so I won't be very strict with it, and when I taught this in the spring, there were definitely times when I took more time in lectures than anticipated, but I can already give you a rough schedule of what's going on, at least chapter by chapter. So,
Okay.
and I'm happy to kind of discuss at least a week in advance, like if you feel advanced, what should you be reading? So I will try to give that information to you.
Okay, thanks.
Yeah, sure. And also there's an attachment by Aaron Willis about how to buy a 381 textbook, which is also valuable. Yes, so here are the sections of Rosen that I plan on covering. Sections 1 and 2 are going to be covered very heavily. They'll take a large part of our time in this course. We'll cover almost all of chapter 1, which is devoted to logic and proofs. This class, and I'll talk more about this when we get to it, this class is not purely a math class in the traditional sense. And what I mean by that is that this class also is kind of a writing class. So what you're expected to be comfortable with after passing this class is a familiarity with the structure of logical arguments and the writing of mathematical proofs. That is the entire focus of chapter 1. And we will do almost no actual math in chapter 1. It'll all be logic and proof writing, which are important skills in and of themselves. So it is definitely the case in this class that you'll be graded sometimes rather sternly on the form of your arguments and the quality of your mathematical writing, which is to some extent independent of your actual mathematical work or mathematical thought. In other words, there are definitely cases in this course where you'll be marked down for having poor mathematical exposition or a incorrect proof or understanding of proof or logic, even if all of your mathematics is correct. It is possible for all the math to be correct, but you still to get points off because you weren't writing things properly, for instance. So that's something to be aware of. And so you should think of this as not purely a mathematics class, but you should pay special attention to the style and form of mathematical proof writing. So that's kind of a, maybe not unique, but an important feature of this class. Chapter 2 is when we start getting into actual mathematics. So we start applying the logic and proofs that we learned in Chapter 1 to sets and functions. And we'll spend a long time in Chapter 2. Then the rest of the sections we will spend less time in. So after logic and proofs and sets and functions, we might mix around and jump around in this order of chapters. I'm not necessarily going to go linearly through the book, but the other topics that we'll cover are number theory, induction, which is a further proof strategy, counting and combinatorics, relations, and we probably will not go into discrete probability. So probably you can strike off discrete probability and think number theory, induction, combinatorics and counting, and relations. That's roughly what I aim to cover in this class. Any questions about this so far? Okay. Grading, there will be 3 midterms. They will each take the time period of a course that is a 50-minute chunk. There will be weekly homework, which I suppose I'm going to start making due on next Monday. So for instance, next Monday on Gradescope, you will all have to turn in homework, and I'll be assigning problems today, Wednesday, and Friday. The grading scheme is 18% for each midterm, 16% for homework, and 30% for the final. Let's check that this adds up to 100. So 18 plus 18 is 36, plus 18 is 50, what, 4? 54, and then 16 will bring us up to 70, and then 30% gives us 100. Great, so I didn't make a math error there. Yeah, this is all reasonable. Any questions before I move on? Okay. Yes. So the online exams, since everything is online, cheating has definitely become more prevalent. I really want to urge y'all against this because it's a massive pain for everyone involved. I've been teaching here for 5 years now. The first cheating that I had to deal with was last semester when things went online, and it was a massive, massive pain for everyone. So I urge you to please resist that temptation. Please follow the honor code. To try to enforce some amount of what's it called when you proctoring. To try to enforce some amount of proctoring, I will be kind of monitoring you on Zoom live during the exams. So the situation will be different if you're in a very different time zone, but if you're in the United States or an analogous time zone, then you will have to take the exam during the class period from 9:20 to 10:10, and you'll take it on Zoom. So you need to show your face as well as your work area. And then what you will do is you will scan or take a picture of the written work and submit it through Gradescope within 15 minutes. And that'll be part of the recorded record. So this is just so that I can try to proctor exams. Any questions about this? I think this is kind of familiar perhaps from last semester or this summer. As of writing, there was not a final schedule up, but we will hold our finals in accordance with university policies. Okay, we're getting to the end here. Attendance is important. As I mentioned, it's very important to get familiar with style and form of answers, not just the answer itself. I don't take attendance, but you should still come. Homework is given on a weekly basis. So I'll be assigning new problems every day, but once a week I will kind of pick up the test sheet, or not the test sheet, your homework where you have kind of written down all these problems. I recommend that you work on problems the day that they are given. Don't try to do a week's worth of problems on Sunday. I really don't advise that or recommend that. Homework is not supposed to be a detriment to your grade. It's not supposed to be a burden. So my policy is to drop the 2 lowest homework grades of the semester. So this should really just, like, the most important thing is that you spend time doing the problems on homework. And you shouldn't necessarily be afraid of a bad grade on a particular homework assignment. That should just let you know that you perhaps didn't understand or didn't digest that particular topic so well, and you shouldn't worry about that as being a big issue, because if you get a particularly low score on some homework, those scores will be dropped. Yeah, so this is kind of a way for me to say, don't worry too much about homework scores. I'm very happy to talk about homework, but I want to talk about problems, and I want to talk about mathematics, not so much about a point here or there. That said, if something is misgraded, by all means, talk to me and we can chat about it. Group study is encouraged. I really recommend that y'all discuss this material with each other. A big part about mathematics is talking about it. I hope that y'all at least know someone else in this class, or you set up a Slack or something to chat about this material, just because it's better to discuss math. But when you're writing up proofs, all of the writing should be your own. So you can discuss a problem and talk about how you want to prove it, but you should be writing your own sentences when you write up a proof. Second, if you have any collaborators on a problem, you should acknowledge them by listing that you worked with them at the beginning of your solution. Failure to adhere to these rules is an honor code violation. And then, yeah, follow the honor code. Please don't cheat. It is a massive pain, and it's easier than you might expect to detect cheating. So, any questions about this long document? No?
I have a question.
Oh, yep.
About the exam, the midterms and the final. Are we expected to have like a second camera, or whatever's on the laptop would be enough to capture?
Whatever's on the laptop is sufficient. I would ask that you place it kind of far away so that I kind of have a larger field of view, so I can see both your face and kind of where you're working, if that's possible.
Okay, yeah, I was just wondering. Thank you.
Yeah, sure, absolutely. Any other questions?
So I have one.
Yeah.
So I'm a statistics major.
Sure.
Is there any reason why, I should like go into on my own time into discrete probability, since we're not really covering that in this class?
No, I highly recommend it. And so sorry, your question blurred out. Were you asking me why I will not go into it, or are you asking whether or not it's a good idea for you to read into it?
The second, whether I should go into looking at it on my own time.
Yeah, so I think that the following is what I would say. When we get into combinatorics, we will be getting very close to discrete probability. My impression is that if that's an important part of this course, so I would love to be able to go into it. It's just last semester I didn't have time, and I don't necessarily anticipate having enough time to do it, but it's quite close to the probability stuff. So I would say, as we enter the probability section of this course, you could probably very easily start reading, or sorry, as we enter the combinatorics part of this course, it would be very easy to read up on the discrete probability side by side and find that the material is very similar. And I'd also be happy to answer questions that you may have about that section if you want to read in that direction. So I encourage reading in that direction. I would say maybe wait until we get into combinatorics and then you'll find a lot of parallels between what we're doing in class and that material.
Okay, great. Thanks.
Any further questions? Okay, so if there are no further questions, then I would like to get started with Math 381. Okay. So the first section that we're going to get into is exactly Chapter 1, Section 1, which is Propositional Logic. Oh, and before I get fully into this, let me say the following. So this is for those of you who are interested in reading ahead, which I recommend, but do not demand. The sections that I will cover in Chapter 1 are 1.1. I will probably not be doing 1.2. I'll be doing 1.3, 1.4, 1.5, 1.6, 1.7, and 1.8. So as far as I'm aware, I will be covering almost all of Chapter 1 with the exception of Section 1.2, which I will essentially skip. Let me just look through this really quick. Maybe I'll do a little bit inside 1.2, but just not the logic circuits bit. So maybe even 1.2. So don't spend too much time here. So if you want to read ahead, go to sections 1.1, 1.3, and 1.4, etc. Okay. So let's get started on propositional logic. So I just want to make a remark too, that logic undergirds mathematics. But it's debatable whether logic is actually a part of mathematics. So we will use it henceforth. Okay. So what I'm saying here is that we won't get to actual math for a while. Definition. A proposition is a declarative sentence So what I mean by declarative sentence is that it declares a fact and it must be either true or false, but not both. So these are the fundamental building blocks of logic. We start with propositions and we build more complicated propositions out of them. And in the end, we are interested in the truth value, so either the truthhood or the falsity of complicated propositions that we build out of more simple propositions. So some examples of some propositions. Denver is the capital of Colorado. So this is it is declaring some fact. It's something that could be either true or false, right? It's declaring that Denver is the capital of some state. And then we can kind of ascertain or determine whether or not this proposition is true or false. Is this proposition true or false? That's a question. It's true, yes. Also, this is just personal preference on my end, but I would be really happy if y'all spoke using your microphones in class, just because otherwise I will go crazy. Just talking to myself all the time. But of course, answering in the chat is also perfectly acceptable. So thank you, Naomi. Denver is the capital of Colorado. It's a proposition because it declares a fact, and then we can determine whether it's true or false. This one happens to be true. It is not false. Another example is Denver is the capital of Brazil. This is asserting a fact in the exact same way that the previous statement was asserting a fact. It's just in this case, this proposition is false. But it's very important that we accept false propositions into our logic. Another proposition is, my name is Mark. This is true.
I have a question.
Yep.
Why would you want to accept a false proposition into your logic if the whole point is for the logic to be logical?
So the thing that we want to, like, we want to be able to construct statements and then be able to detect whether or not they are true or false. So for instance, an important statement in mathematics is something like, all primes are odd numbers. And this is a false statement, and I want to be able to have the statement, all primes are odd numbers. Sorry. So this is asserting some statement about primes. And this statement being false carries mathematical meaning. The mathematical meaning behind this statement is that there exists some prime number which is even. And from the mathematics, I know that that's important because there's a prime number called 2, right? But there's a way of kind of expressing some mathematical validity, or there's mathematical content in this proposition being false. Does that at least provide an example why I want to be able to handle false statements?
Yeah, thank you.
Yeah, absolutely. And this is also very important in other applications of logic. For instance, in building like Boolean circuits or computer circuits. So there you can build up systems of essentially switches that depend on a kind of binary value of something being true or false. And you want to be able to negate a true statement to get something false, and you want to be able to negate a false statement to get something true. So yeah, I hope that this was kind of a helpful explanation. So the system of logic is going to be built around building propositions and then determining whether they are true or false. That was a good question. Any other questions? Can someone give me a proposition that you invent? I'd love to hear a crowd-generated proposition.
I got one.
Yep.
All rectangles are squares.
Yeah, good. And indeed, this is a proposition. It's asserting some fact about rectangles. And is it true or false?
It's false.
It's false. Exactly. Good. So the content of this being false is that there exist rectangles which are not squares, which is something important that we, well, if rectangles are important to you, then it's important. Yeah, very good. Yep.
I have a question. Could you give an example of a proposition that is both true or false, or is that like more of a subjective fact?
So we'll get to those in just a moment, but I want to point out that technically such a thing would not be a proposition. That would be some other kind of statement which has the potential of being both true or false. but we can't handle that. Or what I should say is, the way that we handle such statements is by viewing them in the lens of propositions. And I'll get to that in just a moment. That's an excellent question.
Okay, thank you.
Yeah. So here I want to provide some non-examples. A non-example is do not skip class. This is not asserting any fact, it's just a command, technically, right? What part of speech is the it's been too long since I learned this part of like French. Like there's a tense for command.
I think
What's
it's
that?
imperative, right?
Imperative, perfect, right? This is imperative. In any case, this is some statement that we can construct, but it's not a proposition. And moreover, even if it did assert a fact, this thing isn't true or false, right? Another non-example is what time is it? This is not a proposition because it's not asserting any fact whatsoever. Certainly is not true or false. Here is an example that gets quite close to the previous question. I unfortunately am going to have a tough time with y'all's names, but I will work on it. So I'm not sure who asked the last question about statements which could be either true or false. But here's an example. 4 plus x is equal to 5. This is a very important construction that we will see very often. Technically, this is not a proposition. Because although it's asserting a statement, namely it's asserting that 4 plus x is equal to 5, we can't assess the truthhood of this statement unless we are provided with additional information about x. Does this example make sense? Is it okay or clear why this is not a proposition right now?
So say if we had x equals 1 before, would x equals 1 be a proposition and then 4 plus x equal 5 be another proposition?
I think that almost everything that you said there was correct. So essentially, the point is we can turn this statement into propositions by supplying values for x. So this is not a proposition. But here are two propositions. 4 plus 2 is equal to 5, and 4 plus 1 is equal to 5. Both of these are propositions. And this one is false, and this one is true. So this sort of statement will become very important to us. This is a kind of statement where upon substitution of x, like when we replace x with a given number, then it becomes a proposition. So this is what will be called a conditional statement. So when I put some conditions on x, it becomes a proposition that I can assess as being either true or false. Is this distinction helpful? And does this answer the question about propositions that seem like they can be either true or false?
Yeah, that's very helpful. Thank you.
Yep. Yep. So, and once again, the way that we handle such statements is we provide ways in which it can become a proposition. And then we kind of analyze those propositions one by one, so to speak. Yeah, very good. So we use propositional variables So essentially, I'll be replacing these statements, like Denver is the capital of Colorado, eventually with just symbols like P, Q, R, and S. Okay, so this is kind of adding some symbolism, or not some symbolism, adding symbols into our logic. Any questions on this page, on this discussion? Y'all are asking good questions so far, so I'm happy to answer any further ones. Okay, so the propositions that I wrote down here are mostly what I would call atomic propositions, in the sense that they can't be written in terms of combinations of smaller propositions. So what we're going to do is we're going to start building more complicated propositions out of kind of smaller, more basic propositions. I should have asked this like 10 minutes ago, but is the visibility okay? You should all be very comfortable in telling me when I write something illegible, or when you can't see what's writing on the paper, or anything like that. I'm very aware of the issues that arise here. So please let me know if there's anything I can do to help. Okay. Definition. Let P be a proposition. Here's our first new proposition that we're going to build out of an old one. Then the negation of P which is denoted with this, I don't actually know what that symbol is called. Well, I'll call it the negation. So the negation of P, this is written or denoted by this symbol, and also said not P, is the statement it is not the case that P. So for instance, let's kind of do a little practice. So if P is the statement, Denver is the capital of Brazil, what is the statement not P?
Would it be that Denver is not the capital of Brazil?
Right. I will say it is not the case that Denver is the capital of Brazil. So I say it in this kind of formal way, which is not so important. I just wanted to make it very clear that I'm literally building this statement from P by putting on this clause, it is not the case that, and then having the statement. Of course, you can also write not P is Denver is not the capital of Brazil. Right? So the statement P, Denver is the capital of Brazil, has what truth value?
False.
False, right? And the statement not P has what truth value?
True.
True, exactly. So this is kind of one of the very important underpinnings of logic, is that we only allow P to either be true or false. There's no middle ground, there's no possibility of statements, or sorry, propositions that are not true or false. And then what the negation does to a proposition in terms of its truth values is it switches the truth value. So here we had a true statement, or we had a false statement, the negation is true. If I have a true statement such as P is equal to 2 plus 2 is equal to 4, what is not P? I'll use quotes here so you can see that I'm writing statements.
Would it be that 2 plus 2 is not equal to 4?
Exactly. It'd be 2 plus 2 is not equal to 4. Or if I wanted to write this out, I could write, it is not the case that 2 plus 2 is equal to 4. It is not the case that 2 plus 2 equals 4. Both of these are valid ways to phrase the negation of this statement. And so now this provides yet another reason why we want to permit false statements in our logic, because by the way that we've set it up, the negation of a false statement has to be true. So one statement being false is equivalent to the negation of that statement being true. Is that another, hopefully that's another motivation for why we need to have false statements in our logic. Okay, one way to kind of keep track of the truth and falsehoods, or the truth values is what I should say. So to keep track of truth values, here this means true or false, of compound propositions. So here compound propositions will mean new propositions that we build out of old propositions. So to keep track of these truth values, we will sometimes use truth tables. We can use truth tables. So here is the truth table that relates P and not P. So if P is any proposition, then a priori, I don't know whether P is true. So if I fix any proposition, it's either true or false. But there exist true propositions and there exist false propositions. So if the proposition is true, then that's this case. If the proposition is false, that's this case. And then not P takes the following values. When P is true, what is the truth value of not P?
False.
False. And similarly, when P is false, what is the truth value of not P?
True.
Exactly. So this is a very basic understanding of the relationship between the proposition P and the proposition not P. They take on opposite truth values. Any questions here? So do y'all feel comfortable negating statements? I only did 1 or 2 examples, but should we do more? I can just do one verbally. So let's say the statement P is Vimala's is the best restaurant in Chapel Hill. What's the negation of that statement?
It is not the case that Vimala's is the best restaurant in Chapel Hill, or Vimala's is not the best restaurant.
Right, exactly. A false statement. Okay. So hopefully the negation is okay. We'll be using it a lot, but I probably can't do too many examples right now that show you anything new. One last time, any questions about this? Okay, in the last 5 minutes, we can do one more interesting and a significantly more interesting construction. So definition 3, let P and Q be propositions. Then the conjunction of P and Q, denoted by P and Q. So this is with this upper wedge, P and Q, and red P and Q is the following proposition. Well, it is the proposition P and Q. So for instance, as a basic example, let's say P is the statement 2 plus 2 equals 5, and Q is the statement Vimela's is the best restaurant in Chapel Hill. Then what is the statement P and Q?
Would it be false?
So I'm not necessarily asking right now whether the statement is true or false. I'm just asking, what is the statement P and Q?
2 plus 2 equals 5, and Vimela's is the best restaurant in Chapel Hill.
Yep, 2 plus 2 is 5, and Vimela's is the best restaurant in Chapel Hill. Note here that these propositions have nothing to do with each other, absolutely nothing to do with each other, but you can make the conjunction of any two propositions that you want. The content of the propositions essentially doesn't matter at all. All that we're doing here is building new statements out of old. And now the important point is we want to understand the truth values of this compound proposition. Okay? So, and this goes exactly to the answer that someone just gave me, saying that this statement is false. That is indeed correct. And I want to explain why. So the proposition P and Q is true when both P and Q are true and false otherwise. And this is, I think, pretty plain to see. If you're trying to assess the validity or the truth of this statement, 2 plus 2 equals 5, and Vimela's is the best restaurant on Chapel Hill, what you do is you examine both of the individual statements. First of all, 2 plus 2 equals 5, and separately, Vimela's is the best restaurant in Chapel Hill, and then you'd only say that this proposition is true if both of the constituent statements are true. So in this case, this is false because 2 plus 2 is equal to 5 is a false statement. In other words, I can set up a truth table. So here's the statement P, here's the statement Q. If I fix a statement P, it's either true or false. If I fix a statement Q, it's either true or false. But in general, I want to be able to handle all those combinations. So my truth table will look like this. I want to here write down all the possible combinations of possibilities when P is either a true statement or a false statement, and when Q is either a true statement or a false statement. And there are 4 possible combinations, both true, one true, the other false, the opposite, and then both false. And then here, I can write down the truth values of P and Q. It is going to be true when both P and Q are true, and it'll be false in all other cases. So the point is that I have constructed a compound proposition whose truth value totally depends on the truth values of the constituent parts. So this is a compound proposition. Let me do just one last brief example. Oh, it's 10-10, so I'll do one very brief example. Here's an example of a true conjunction. 2 plus 2 equals 4, and it is semi. So this is the proposition built out of P and Q. And this is a true proposition because 2 plus 2 equals 4 is a true proposition. And second of all, at least where I am right now, it is sunny, this proposition Q, is also true. Since both of these propositions are true, the conjunction of the statements is true. But if either of these are false or both are false, then the conjunction of the two statements is false. So for instance, 2 plus 2 equals 5, and I like to, well, no, let's do something better than that. What's another, and Denver is the capital of Brazil. This is a false statement, and it's false because either P or Q, one of these statements is false. Sorry, you can't see. It turns out that both of these are false. So this whole statement is false. Okay, it is 10:11. I have held you 1 minute over on the first day of class, which is a terrible precedent. Have a wonderful day, and I'm around to ask if you have any questions. Also, I have office hours today at 10:30. So yeah, have a wonderful day, and any questions?
Thank you.
Yeah, sure.
Thank you.
Thank you.
Thank you.
I do have one question.
Sure, let me stop the recording briefly, and then I'd be happy to answer.